Hey guys, let's discuss round 2 of Apple interview loop, and which is called coding round 1. So here we will be seeing coding question. Okay, so the coding question you have given is implement a file system. You need to implement file system like you have the directory, then inside that you have a folder, okay, subfolder, and then inside you will have a files, and so that kind of file structure you need to implement. Okay, fine. So see, the design and implement a file system similar to lead code design file system. Okay, so lead code design file system also you can say. The system should support basic file and directory operations. Now, what is that? So let's say the functional requirement you have given is the file system should support create directory, okay, then create file, read file, write or update file, delete directory, check whether a path exists, okay, and then list directory content or handle nested directories. So for example, something like this, you can see you have a user folder, inside that you have a Chetna folder and then LX folder, and inside Chetna you have a resume.pdf, notes.txt, and then inside LX you have photo.jpg, then you will have a system folder also, so something like this, then config.js. Now what will be the non-functional requirement here? So see, the efficient file lookup. First of all, efficient file lookup, what does that mean? Finding a file quickly without scanning the entire file system, okay, then efficient directory traversal and correct path handling. So for example, let's say you have given path something like this, and you know that when you see double dot, right, double dot, so it means that you have to come out from the current directory. So should correctly resolve something like this, right? First you were in home, user and docs, now you came out from docs, so the path would be home, user, and then file.txt. Okay, so now next non-functional requirement is thread safety. Okay, multiple user can work concurrently. Then data consistency, large directory support. Okay, if the directory is very large, it has millions of file, it has lots of folder. Okay, then also it should support. In that case, we will be using distributed system. Okay, and fault tolerance and scalable storage. So now what software engineer will say, he will say that I would represent the file system as a tree. Now here let me tell you, if you don't know, the real life example of the real life, in the sense in a IT example of technology example of tree is your file system. So let's say you have a parent directory which is your root node. Okay, now inside that you have a two folder. Let's say it is a Chetna folder and then user folder. Okay, so this is also one node itself. Then inside this, let's say you have a resume.pdf, one more folder, okay, like system, and that one will also be, so means directory will be the node. Okay, and then let's say it has the some config.js. Okay, so something like this. So this is the example of a tree. Okay, the file system is the example of tree. What is the example of graph? Facebook, right? One person is connected to another is connected to third one is connected to first one. So that is also graph can have a cycles, right? So that is the example of graph. Okay, so what software engineer is saying here, I would represent the file system as a tree. Each directory would contain a map of child names, okay, to file or directory node. See, inside one directory, either you can have a directory or a file, right? Nothing else. There is no third option. Either you can have a directory or a child, right? So I'll create one map which will have the file name and then one directory node. Okay, we will see the structure. We'll see the Java code also at the end. Okay, a path can be split into components and traversed through the to the node. Okay, from the node. For example, if you wanted to traverse here, so you will come from the node, and this one will be your path. This gives efficient lookup while keeping the implementation simple. This is the high level design. You can see the root node, then user and system folder, then Chetna folder. Inside that you will have two files, right? And this one file system node. So this is the node, okay, this node, and the structure of this node would be name. Okay, either you can have a directory name or you can have a file name. Now is file, okay, which will check whether it is a directory or a file, because node can be directory or it can be a file. Okay, then content. So if it is a file, you will see the content there. Otherwise, if it is a node, then in that case the children would be of type map, where you will have the file name and then file system node again, once again. Fine. So for directories, let's say children equal to map string comma file system node. This is what we have seen. Now for files content, okay, of type byte array. Okay, senior software engineer, what he will be saying that I would implement the file system as a tree, where each directory maintains a map string comma file system node for fast child lookup. I would add thread safety using read write lock. Path normalization. Path normalization we have seen. If you have a dot dot, then you should give the correct path. Okay, just come out from that directory and what will be the correct path. Then pagination for large directories. Okay, let's say directory is very large. It has a 10 millions of record and you are fetching first 100 record, so it should not fetch all 10 millions record. Okay, first it should fetch 100 record, then cursor will point to 101 record. Okay, and then again it will fetch next 100 and then cursor will point to 200, let's say 201 record. Okay, 200 first record. So so something like that. So pagination also it should support. And then metadata caching. Okay, metadata caching means one file everybody is using it, so the metadata of the file, like file size, timestamp. Okay, content is not the metadata. Content will store in S3 bucket, let's say. Okay, and the metadata information will store in the database. So metadata caching. After that, lookup would be order of path depth. I would also handle concurrent read writes, recursive deletion, and proper error handling. Recursive deletion means I wanted to delete one user folder. So inside that user folder, whatever I have, I will first delete that, and then I will at the end I will delete the user folder. So that is the recursive deletion. Okay, now principal software engineer, what he will be saying. At principal level, I would evolve in-memory tree into the distributed file system. Okay, again he is saying the same thing. Initially we were using in-memory, but now your directory structure is very large, very huge. So it will you have to store in the multiple servers there. Okay, now I would separate metadata from file content, store large files as chunks in distributed storage, partition metadata for scalability, and use replication for fault tolerance. I would also consider multi-region deployment, consistency, versioning, snapshot, security, and disaster recovery. Okay, step 3 is core operation. Okay, so now core operation, what all core operation would be there. So first one is create directory. Okay, make directory. So traverse the path and create missing directory node. Okay, so make directory user comma chetna. So it will create first a user directory and then inside that it will create a chetna directory. Now create file. Okay, so it will add the file as a child of the parent directory. Read file is the another operation. Okay, so first one we have seen create directory, then create file, then read file, then write file. Okay, again write file and update the content stored in the file node. Okay, then delete file also there, or delete directory, remove node from its a parent directory, so remove directory, that is the thing. Okay, now let's talk here a few follow-up questions. So first one is CRUD operation. We have already seen CRUD operation, right? Create, read, update, delete. So it will be something like this: create, read, update, delete. Okay, then each operation first resolve as the path and then perform the requested operation. So first you will resolve the path whether that directory or file is there or not. Okay, it will check all those things. Now second follow-up question is time complexity. So see, we have not seen it for software engineer, senior software architect. For everybody the CRUD operation would be common, right? So that's why. Next is follow-up question, time complexity. So how much time it will take? So see, let D is the number of directories or component in the path. So path lookup will be order D, right? So like for example, this is your tree and you need to find this one. So what will be your complexity? This node, and this node. So you have traversed this path, right? This path. So order D, where D is the path length. So if each directory uses hash map, looking up child is approximately order 1, right? You have already stored this, no, this children, this and its children is this one. So from map you will just get it. So order 1. constant time. Now therefore path traversal is order D, and then reading or writing C bytes from the file content additionally requires approximately um, order C time. Okay, now senior software engineer, what he will be saying that let D is the number of path component and C is the file size. Okay, so with a hash map at each directory, path traversal takes order D because each component looks up order 1 on average. Okay, so reading or writing the file content adds order C, so overall operation is order D plus C. The principal software engineer, what he will be saying, at principal level, I would separate metadata lookup from file content access. Okay. Um, then, so metadata would be different and then file content would be different. He's talking about the same thing. Metadata path resolve order D with indexed or sharded metadata for a file size C, reading or writing the entire content order C. Okay, and although chunking also parallel and partial access. Okay, so you can, if you have a very large file, just chunk it, so parallelly you can read that file. Okay, with different chunks. So the basic complexity is order D plus C, while distributed storage adds network replication and coordination overhead. Okay, now follow-up question 3 is edge cases. Okay, so edge cases, what all edge cases or test cases you will see here. Okay, so software engineer will say he will handle the empty path, then root path, duplicate file, duplicate directory, file inside a file, reading a directory as a file. Okay, then deleting a non-existent path, invalid path, trailing or multiple or empty path. Okay, so for example, read file and then user. Okay, so it will first check that should return error because slash user is a directory and not the file, so it has to check all these things. Now senior software engineer, what he will be saying, I would explicitly validate the path and node type before every operation. I would handle root and empty paths. Okay, then normalize trailing or duplicate slash at the end if you have a slash or a duplicate slash, so you need to handle that separately. Then reject duplicate files or directories. Okay, prevent creating a child under a file. Inside file you cannot create child again, right? So and return proper error for non-existent paths. I would also distinguish between file and directory operations. For example, read file users should return a not a file error. Now what principal software engineer here he will say, so at principal level I would additionally define consistent error semantics and path rule across distributed services. Okay, so path rule between distributed services, so in each server it should follow similarly. Okay, with the same rules. Now, path normalization should happen at the API boundary, and operation should be idempotent, okay, where appropriate. I would also handle concurrent create or delete operations, so two clients cannot create conflicting entities or accidentally delete a newly created resources. Okay, now what is follow-up question for error handling, right? So, what will be the returned error? Path not found, already exist, not a file, not a directory, invalid path, and then permission denied. The implementation should avoid slightly ignoring invalid operations. What senior software engineer will say, I would define explicit error code for each failure scenario instead of silently ignoring errors. Okay, same thing he's saying. For example, path not found when the path doesn't exist, already exist, duplicate creation, not a file when a reading directory, and then not a directory when reading operations are performed on a file. I would also validate paths and check permission before modifying or reading data. So check permission also you need to check, right? Whether you have a permission to execute that operation on that particular file. The principal software engineer will say, I would use the same standardized error model, but ensure errors remain consistent across distributed services. The API layer should translate internal failures into stable error codes, while operations should be idempotent where possible. I would also distinguish retrievable error, such as temporary storage failure, from a retriable error like invalid path or permission denied. See, if permission, you don't have a permission or the path is invalid, so you cannot retry it. Okay, if you retry it, nothing will happen. But if the temporary storage is not there, so you can retry that, because next time maybe it is empty, right? Now follow-up question 5 is thread safety. So see, multiple users are working on your file, let's say at the same time. So software engineer will say that multiple requests may access the same file or directory simultaneously. So you use read lock, write lock, okay? Then fine-grained locking. Now what is fine-grained locking? Just lock the particular section, okay? And then so other services can use perform operation for the other part. And then atomic operation. Multiple reader can execute concurrently while writing requires exclusive access, okay? So reader can read it, but writer would be required lock on that particular section. Okay, so senior software engineer, what he will be saying that I would use read write locks to make the file and directory operations thread safe. Multiple reads can happen concurrently, while write require an exclusive write lock. I would prefer fine-grained locks at the file or directory level rather than one global lock. So unrelated operations can proceed concurrently. Operations like create, delete and rename should be atomic. What is the example? Let's say read file, okay? So read lock use. Or if the operation is write file, so use write lock, okay? If it is a delete or create, then again use write lock there. Now, principal software engineer, what he will be saying, at principal level, I would first define the concurrency model and locking scope. Okay, so what concurrency model you're using and what is the locking scope. For a single node file system, fine-grained read-write lock works well. In a distributed system, local logs are not enough. Okay, so if the one machine you have, so you can use the logs, but you have multiple machines, so every log will be the local to that server only. Okay, so you need a one mechanism which will work for the distributed system. Okay, so I would use distributed locking or optimistic concurrency with version numbers. So he will use version number also here. Then metadata updates such as create, delete and rename should be atomic, and we should avoid holding locks during slow storage operations. Now follow-up question 7 is directory indexing. Okay, so software engineer will say a directory containing millions of files cannot efficiently be managed using the simple linear list. So for ordered list, use balance tree or B tree. Okay, we will use the B tree because you have a lots of millions of files there, so you cannot use any linear data structure or list. Okay, let's say array list, so there you will be using B tree or balance tree. So we will see what is that. We use the concept of range there. Okay, so this provides efficient lookup and scalable directory operations. What senior software engineer will say here: for a directory with millions of files, I would avoid a linear list. I would use a hash map keyed by file name for fast lookup. Okay, we will see Java program on based on the hash map, okay, and not the B tree. For theory, you just read about the B tree. Okay, so giving approximately order one average lookup. If we need sorted listing or range queries, I would use B tree or binary tree. I would also paginate directory listing. Okay, so if you wanted to use sorted list or range queries, then you go with the B tree. Otherwise, we will use the hash map. Principal software engineer will say at principal level, millions of entries may exceed the capacity of a single machine. I would partition or shard directory metadata, access multiple nodes typically using a directory ID. And file name hash. Each shard can use an indexed structure such as B tree or LSM based store. Directory listing would use pagination and cursors. A B tree is a tree data structure that keeps data sorted and stores multiple keys in each node. Okay, in each node it stores the multiple keys. So example something like this. Let's say you have a D and M. In one node you have a key D and then M. Okay, then for D, let's say you have a two nodes, A and C. Range, can you see range? See, So if it is alphabet is lesser than D, it will come to this part. If it is greater than M, then will come to this part. Okay. Now D is again divided into two parts, A and C. Then E and L, where E and L will come. So D, E will here, M. Okay, E and L. Then N and Z will also come here. So something like this, then we will use the concept of range, and in one node you can store multiple values. So if you search k.txt, you know that you need to go E or L section instead of checking the entire file. So now follow-up question 8 is large directory and optimization. Let's say you have a very large directory, then how you will optimize it? So software engineer will say that for very large directory, partition directory metadata first of all, okay, then use indexed lookup, avoid loading all entries into memory, then support pagination, cache frequently accessed entries, and then use lazy loading. Instead of list of video, okay, and then load 10 million files, just give the limit there. So it will just search for the first 100 records only. Senior software engineer will say for very large directories, I would avoid loading all entries into memory. I would use indexed lookup, pagination, lazy loading, and caching for frequently accessed entries. Okay, directory metadata can also be partitioned to improve scalability. Principal software engineer, he will be saying that at principal level, I would design large directories as a distributed metadata problem. I would shard directory and entries across nodes. Okay, means he will distribute it to multiple servers and use distributed indexes and use cursor-based pagination. I would also handle hot directories, metadata caching, and load balancing and replication. All big words he has used here. Now follow-up question 9 is metadata caching. How you will cache the metadata. Metadata, what all things will come, like file location, file size, permission, modification time, directory information. These all things will come to file metadata. So cache frequently accessed metadata such as this, and use TTL and invalidation when metadata changes. Okay. Now what senior software engineer will say here, he will say that I would cache frequently accessed metadata such as file location, size, permission, modification time, and directory information. On a cache hit, we return immediately. On a miss, we fetch from metadata store and populate the cache. The same thing he is saying. I would use TTL and cache invalidation when metadata changes. Now what principal software engineer will say? So he will say that at principal level, I would design a distributed metadata cache. I would consider cache consistency, eviction, replication, and handling hot keys. Okay, hot keys means the data which is getting used more. So lots of people are accessing that data. Now update to metadata should invalidate and update all relevant cache entries, and I would prevent stale data from causing incorrect file operations. Follow-up question 10 is concurrency problem. Okay, so let's say you have a two client. Client A is writing ABC, client B is writing XYZ on the same file. So software engineer or senior software engineer both, okay, will say that without synchronization, the final result may be unpredictable, right? So means write first you will have a write log that then it will update, and then you will have a release log. Okay, then another person will write. So for distributed system, local logs are not enough. We would need distributed coordination mechanism. Now architect or principal engineer, what he will say, at the architect level, I would evolve the local tree based file system into a distributed storage platform. Okay, metadata and file data would be separated. Storage would be distributed across nodes, and replication, snapshots, versioning, disaster recovery, and multi-region availability would become first-class capabilities. The follow-up question 11 is distributed file system. Okay, so what metadata you need to separate file name, directory, permission, owner, file size, version, location from file data. Okay, file data you will store in the AWS S3, let's say object storage. Actual file content, metadata can be stored in the distributed databases, while large file content is stored in the distributed object or block storage. So this allows both layer to scale independently, metadata also and then file content also. Okay, now follow-up question 12 is file storage. Uh, this question has a lot of theory, right? It's a very lengthy actually. So, okay, follow-up question 12 is large file should be splitted into the chunks. Okay, so like chunk 1, 2, 3, one video.mp4 you were having, and then you have splitted into the chunks. Chunk can be distributed across storage nodes. So benefits: parallel read write, large file support, independent replication, better fault tolerance, and then easier recovery. That's why. Okay, so all these things you can use if you chunk the files. Follow-up question 14 is consistency. So architect or principal engineer will say, everybody will say that different operations may require different consistency level. For example, file metadata, strong consistency would be required. But if it is a file content or large media replication, then you can go there with this eventual consistency may be acceptable there. So the design should avoid using strong consistency everywhere because it is increases latency and coordination cost. Follow-up question 15 is snapshot support. Okay, so you take a snapshot also time to time. So architect or principal engineer will say a snapshot represents the state of the file system at a specific point of time. For example, 10 o'clock you took one snapshot. Okay, 11 o'clock you took file changed. Let's say 11 o'clock file changed. So at 12 o'clock you took another snapshot, which is second. So use copy on write. So unchanged blocks don't need to be copied. Now, block A is shared, block B is shared. Okay, snapshot. Now block C is the new one. So you will just take the snapshot of the new one only, and if it is not updated, okay, then just use the last one only. This makes snapshot storage efficient, right? Okay, now let's see Java code. Java code is very simple actually. Okay, this is the your file system class, main class. Inside that you have one static class which is called file system node. Now if you remember the node structure, okay, it was having name, then is file boolean, whether it is a file or directory, then it's a content, okay, which is of type string, and then then again that node map, right, string comma node, which is your children. Like this is the node and then it's children here. So this one is one node. This one will also be one node, but it will have the string comma the address of the node. Okay, so string will be this, maybe parent node. Okay, so now this is the normal constructor. Okay, here it is checking if it is a file, then content will be empty initially, otherwise it will go to children and create a hash map. Okay, if it is a file, then this. If it is a directory, then this. Now private file, file system node. Okay, first you will create one root node, and then you will just with this file system constructor, you will just initialize that file system node, okay, with value false initially. Okay, now let's see few operations like create directory, the very first thing. Okay, so mac directory, mk directory, so you just give one path there, okay, in mac directory, and so that path first of all you will normalize it. Okay, if it has a dot dot slash, then it will come out from one directory. So just create one proper path, and then you just split it into the array, so you will have a parts. Now let's your current is pointing to root. Okay, you have something like this. So current is pointing to root. Initially this was the root. Okay, this is a normal tree question and nothing. Now you will iterate that parts array. Okay, and if it is a file, then you will say that illegal argument exception, not a directory. You need directory to traverse, right? And otherwise it will go to then it will check that current children dot contains the part. Okay, if that part is there in the see, if this path is there, this part is there. Okay, so you will just go to next part, next children, right? If it is not there, then you create it, right? That is what normally we do. If you give one path and that path folders are not exist, so it will create the folders, and then inside that it will create the file, right? So the same thing we are doing here. If it is not there in the path, okay, so it will put that into the children, otherwise it will go to next children, right? Now create file. If you wanted to create a file on particular path, okay, so again it will find the parts array, and it will check if the part is 0, then it means that invalid path. Okay, you need to check the invalid path also, different error codes. Now otherwise you will get the node for that particular path. Okay, what we are doing here, we are creating the file. So once that parent.is file, if it is a file, then just say not a directory, and string file name. Okay, first you take the file name, and then parent.children.contains key file name. If it is there, then just throw the exception already exists, right? It should not be there, then only you will create a new file. Otherwise just put that file with the file name. Very simple. Now see the read file, how you will read the file. So let's say you have given one path, and then you will get the node. Okay, that particular node. If node is null, then just say path not found. Otherwise if node.is file, it is not a file, then in that case say not a file. Okay, otherwise return node.content. Very simple. Next operation is write file. So same. Okay, path and content you have given, you will get that node. Check if it is null, path not found. If it is not file, say not a file. Okay, otherwise node content equal to content. Check path exists, whether that path exists or not. So just get that node. Okay, first normalize the path and get node. If it is null, if it is not null, then it is exist, otherwise it doesn't exist. Okay, now list directory. So if you wanted to list all the directory of that particular path, how you will do that? So you just get the node. Okay, and then check node equal to null, so path not found. Otherwise node.is file. Okay, so not a directory, correct? Else you just create one array list, and just get all the key set, node.children.key set, because here you are using the map, right? So we'll use that function, map function key set, and then sort it, and then just return the result. Now if you wanted to delete a file or empty the directory, how you will do that? So you have one path. Okay, you normalize that path, will get the parts. Check if it is null, then invalid path. Otherwise it will get that particular node or the parent. Parent is null, then path not found. Okay, otherwise it will get the name, and then get that children from that parent. Okay, if it is null, then path not found. Otherwise only allow deleting empty directories. So node.is file, if it is not a file, and then the children is not empty, in that case just throw directory not empty. Okay, so you cannot delete the content without asking directly. You will delete the directory? No, that is not possible, right? So that's why this check is here. Otherwise parent.children remove that particular directory. Helper function like get node. Okay, we have seen this. If you wanted particular node, this is parts. So first your current will point to root, and you will iterate this parts array. Okay, then you will check that current.is file, then null, few checks, right? Otherwise current equal to current.children.get part, just go to that, traverse it. Okay, and at the end return current. So very big program. Okay, lots of, actually it has a lot of functions, that's it, but the functions are very simple, right? So find parents based on number of components. So let's say get node. Okay, you have given parts and then length. So your current is pointing to null, so root. Okay, and then just check, so iterate one for loop till length, and check current.is file, then return null. Otherwise go to that node, and then return that node. Okay, normalize where you have to check double dot, slash, and all those things, right? So those rules are here. You have given one path. If path is null or empty, then just say invalid path. Otherwise just convert that, split on the basis of slash. Okay, and you will have a string array row parts, and then create one array list. Okay, then iterate that row parts, and just handle this slash and double slash. Okay, so how you will handle this slash and double slash? You'll check if it is empty or it is equal to dot. Okay, then continue. Otherwise if it is dot dot, okay, if it is dot dot, then in that case if part is equal to dot dot, in that case if part is not empty, so you just remove part size -1. The first one just means just parent one, right? And then continue, and then add at the end add the part into the array, because you have deleted the above one, but that one you have to keep in the path, right? So that is what you are doing. Main function, you have created file system object. Okay, then you have created, means you have made the directory, You will create a file, then you will write a file, okay, then you will sys out this resume.pdf file, okay, then again this Chetna folder, so it will list all the files inside that. It will check whether this file exists or not, okay, it will delete this particular file, then again it will check whether this file exists or not. So that's it. Thank you.